Good evening everybody. Today we will just see how the different metal ions are reacting with the ligands and the type of reactions what we can have. So, the nature of reactions, we can also talk all these things in terms of not only the reactions, but the reactivity as well. Because if we have certain metal ions, say Fe3 plus or Ni2 plus, and in a broader sense what we will see that how this can react with the different types of ligands. And when it forms, basically we see initially if they are distinguishable from a color change. So, there will be a color change for this particular reaction, and in all these cases what we can see that the corresponding metal ions which are present as in aqueous solution is mostly the corresponding hexa-aquo compounds or the corresponding tetra-aquo compounds in solution. So, in a true sense what we will be talking about that the corresponding reactivity of these aquo complexes when water is the reaction medium with that of our ligands. So, we see some color change, that means the metal ion is reacting with the ligand and we get the corresponding interaction with that of metal with that of our ligand. And if there is a solubility difference, that means if the corresponding complex and the nature of the ligand can also tell us that what type of solution we should use for the ligands also. So, sometimes we see that if some big organic molecules are there as the ligands such as bipyridine or orthophenanthroline, they are soluble in non-aqueous medium such as alcohol or acetonitrile or dichloromethane. In that particular case, if we add the corresponding water solution or aqueous solution of the metal salt, there will be color change, and some processing for that solution we ultimately get the solid product. So, we can have in our hand the corresponding solid product and we can analyze everything and we know the nature of the corresponding complex if we find out the corresponding X-ray structure and all other spectroscopic properties we can use to characterize that particular metal complex. So, what type of ligands we can have, that will tell us about the reactions and the reactivity of these metal ions with the ligands, such that ultimately we can propose some mechanism for those reactions. Because since we consider these hexa-aquo or the tetra-aquo metal ions, they are also in some form they are also metal complexes. So, these metal complexes when they are reacting with any other ligand, say these are reacting with say ammonia molecules, this is also reacting with ammonia molecules. So, when already we have 6 water molecules surrounding the metal centers, so these are our water molecules. So, we have 6 water molecules surrounding this metal ion, and what we find that these ammonia molecules will come and basically substitute these water molecules. So, we can compare the corresponding reactivity pattern of this ammonia and water, because why this water molecule will leave the coordinate sphere of say iron or nickel when ammonia is coming to replace the corresponding water molecule as their original ligand. So, what we find in terms of the corresponding reactivity of these aqua complexes, we find it as the corresponding ligand substitution reaction. So, we will have this as ligand substitution reaction, and what are the different types of steps we can have, and how this mechanistic thing, because it can have two aspects, one is the kinetic aspect and another is the thermodynamic aspect. What more information we can have for the process of substitution of all these reactions, and this particular water molecule is replaced and we are adding ammonia, that means the addition of these ammonia molecules also we can see. So, before starting that particular aspect, that means the mechanism of this reaction, we will finish little bit remaining for these nature of these ligands. That means the nature of the ligands are also very much important to control these reactions, this reactivity pattern, and ultimately the mechanism of all these reactions. So, the nature of these ligands, that means we are talking all in terms of the corresponding spectrochemical series, and if we just simply see that how we can compare these two and some more within the spectrochemical series, whether this water will be replaced by the ammonia or ammonia will be replaced by these water molecules. Because when in some other compound the coordinated groups are all are ammonia. So, 6 ammonia groups are attaching to the center, and if this particular center is our say cobalt center, so it is nothing but hexaamine cobalt 3 cation. So, which is pretty stable we all know, and it can be prepared from cobaltous chloride very easily. So, this has all hydrogens. So, what we can study for this compound is that whether we can go back it, that means whether these ammonia groups can be replaced by these water molecules. So, that is also dependent on the nature of the central metal ion and how strong this particular bond and its corresponding heat of reaction or enthalpy of formation for this cobalt nitrogen bond, where the nitrogen belongs to this ammonia molecule, because this was we are talking with say iron or nickel, but in this particular case it is cobalt. So, whether water can replace these ammonia molecules, that we can check, and for that also we can see or we can check the corresponding reactivity pattern with say some proton donor, that means some acid or some weak acid. So, if we have some weak acid in our hand, and what will happen there basically the very interesting reaction in that way, that this particular proton will come and it will take out these NH3 plus H plus, and we will just lose some ammonium ion. And when you lose some ammonium ion, and since we are giving some amount of proton into the system and which is the acidic in nature, so in that particular case this water molecule will come and occupy this position. So, it is basically triggered by the addition of these proton. It is not that if you simply do this reaction, because we are doing all these reaction, the entire reaction, and if we go for the corresponding isolated compound, corresponding isolated hexaamine cobalt 3 compound, and if we just simply dissolve it in water, what we should expect? We expect that if there is direct substitution of this ammonia group by the water molecules, it can, if it can happen with this also, then ammonia groups can also be replaced by these water molecules. But this is not happening. We need the corresponding addition of the proton to the system such that your ammonia groups are protonated, and we leave this as ammonium ion, and this water molecule will come and occupy some of these positions or all of these positions around this octahedral cobalt ion to give us the corresponding hexa-aco compound. So, the remaining part what is there for the nature of these ligands, what we have seen that the pi acceptor ligands what we are talking about, because this particular thing will tell us about the corresponding nature of this metal ligand bonding strength, how strong they are, and how quickly we can remove this ligand from the environment of this particular metal. So, what happens if we have some pi orbitals and also that orbital is the pi star, that means the antibonding orbital which is available for acceptance of electron density from the metal side. We call all these ligands, we group them, these ligands can be grouped as good pi acceptor ligands. So, they are there, so such as Cn minus, dinitrogen and carbon monoxide, they have empty pi antibonding orbitals, that means pi star orbitals are available of proper symmetry and energy. Because when we draw the corresponding molecular orbital diagram, we see that the energetically if they are matched, then only we have the good electronic charge transfer from one particular level to the other. Otherwise, if the symmetry is not matched, we do not have any good overlap from the site where we have one particular type of metal giving the corresponding molecular orbitals of right symmetry and the ligand group orbitals of that particular matching symmetry. So, if the symmetry is matched and the energy is also favorable, energy matching is also favorable, then the corresponding d orbitals can interact, which is present on the metal side, which interact with the corresponding empty orbitals on carbon monoxide or Cn minus to show the behavior for the corresponding pi acceptance. So, this is the field 1, and already we have seen in one of our earlier transparency that this is the carbon monoxide molecule with this particular symmetry level which is not matched, that means this overlap is for antibonding orbital formation. So, this is the antibonding level on the carbon monoxide molecule, and if the electron density is pushed from here to the carbon monoxide, we get the corresponding acceptance. So, if we see that the corresponding molecular orbital picture for the ligand itself. So, if we just simply consider the corresponding molecular orbital picture of the carbon monoxide, which is providing us the corresponding number of electron, carbon is providing us 4 electrons and oxygen is providing us 6 electrons. So, altogether 10 electrons we can have, but not that all electrons are donated to the metal center for the formation of the metal carbon bond in the corresponding carbonyl complexes, because there are a large number of such metal carbonyl complexes are there, such as nickel tetracarbonyl and others. But in this particular case, if we see the corresponding molecular orbital picture for carbon side and that of the oxygen side, because oxygen side is having more number of electrons. So, the 2s level and 2p level are stabilized more, and on the left hand side we have the 2s and 2p from the carbon side, and these 2s when they are having the matching symmetry with the 2s of the oxygen side and 2px, basically which can give, we all know that corresponding sp overlap is also allowed, because the px orbital, if the bonding axis is the x axis, then the px orbital can nicely overlap with the 2s orbital of the carbon, and this particular case, that means the px of carbon can also overlap with the px of oxygen. So, we have for 1 sigma level which is between 2s interaction, then the corresponding 2 sigma, also this is the corresponding bonding level and this is the antibonding level for interaction with the 2s, because with respect to these 2s this is higher energy. So, that is basically the antibonding level. So, the corresponding antibonding level which is having the symmetry level is sigma, and it is also filled and which is of lower in energy compared to the 2s level of the carbon atom. Then we are having the px and py orbitals, and these px and py orbitals have matched symmetry for the corresponding pi interaction, and then we can have the px-px interaction which is also of sigma type. So, when this px-px interaction from the carbon side to that of the oxygen side giving the 3 sigma orbital, because this numbering is only for the ordering such as 1 sigma, 2 sigma, 3 sigma, 4 sigma, this energy ordering, the ground one is the lowest one is 1 sigma, and the highest one is 4 sigma. Similarly, in case of pi also it is 1 pi and it is 2 pi. So, it is a very simple diagrammatic picture for the carbon monoxide molecular orbitals. So, we have the field 3 sigma level. So, this 3 sigma level has some overlap from the S level, but mainly it is forming from the px interaction from the carbon and the oxygen. So, if we have the corresponding orbitals like this, that means this is the matching orbital from carbon side as well as from the oxygen side, and when we have the 3 sigma level and this 3 sigma molecular orbital which is filled with electrons, and this the bigger lobe which has been shown over here from the carbon side can be donated these 2 electrons to the metal ion. So, this metal ion what we are talking about is nothing but the corresponding metal in 0 oxidation state, because we know that the nickel is forming in 0 oxidation state. That means, the nickel is in metallic form, and we all know if we have the finely ground or finely powdered nickel in our hand, and if we pass carbon monoxide gas on it, and we will be able to produce through the Mond process. The Mond first discovered that particular thing, that we can have the corresponding tetracarbonyl complex of nickel. So, we have from the carbon side we have the lobe, and which is basically donated to some of the empty orbitals on the nickel atom. So, nickel is in 0 oxidation state. So, most of them are filled now because it is in the 0 oxidation state, but there are some higher energy orbitals available on nickel which can be utilized for the acceptance from the carbon monoxide side. So, we have the highest occupied molecular orbital which is the HOMO here in this diagram. So, we have this HOMO in our hand, and which is of 3 sigma type. So, this HOMO will be utilized for the donation. Now, what about this carbon monoxide molecule which we are classifying it as the good pi acceptor ligand? So, these pi acceptor ligands will be of 2 types. That means, is that we have the 2 pi orbitals which are of pi star symmetry. That means, they are antibonding corresponding to this level, which is 1 pi, and this is 2 pi. That means, involving px and py, this is also involving px and py. So, this if these 2 are in px level, that means it is in the y direction, which is in the plane of this terminal, and which is perpendicular to this is the corresponding pz. So, px already utilized for sigma interaction, then py for 1 pi star and pz for another pi star. So, these orbitals will be utilized for acceptance of electron density from the metal. So, these are behaving as a LUMO, that means lowest unoccupied molecular orbitals. So, unoccupied molecular orbitals will take off the electron density, will receive the electron density from the field level of say nickel 0, because the nickel 0 already have all the field levels in the d orbitals, and if we have some matching symmetry with these LUMOs, then we can have the overlap, and the electron density can be transformed from the metal side to the ligand side, and the ligand can behave as a good acceptor ligand by accepting the electron density in their pi levels. That means, they are in their pi star level. So, this is the basic diagram for that. When we have this, that means, when the corresponding 3 sigma level is utilized for donation, that means, this orbital is utilized for donation to the metal side, and these orbitals are utilized for acceptance. So, this is the sigma orbital from the carbon monoxide side. So, the carbon end is basically utilized for donation. So, this yellow lobe basically on the carbon side as well as for the oxygen side is utilized for the donation to the metal side. And the metal side, if we have some higher energy orbitals which are of this particular axis, that means, if we have the corresponding px, py or pz or dz square or dx square minus y square, which are only pointing towards the Cartesian axis. So, these orbitals, if they are vacant, then only it can receive some amount of electron density in terms of their sigma orbital. So, this sigma donation is very weak in case of carbon monoxide, what it is there. So, this weak carbon monoxide sigma donation is basically facilitating the second step, that means the synergistic effect, which basically gives us the corresponding thing that if we can have some electron density of this antibonding level of this carbon monoxide molecules. So, if this antibonding level we can have and they are basically vacant. So, electron density can be pushed from the metal side. In this diagram we will be elaborating that. So, electron density can be pushed back. So, this can also be considered from carbon to metal and metal to carbon. So, this thing basically we consider whenever we are talking a metal ligand interaction, but the situation has now been changed where the metal ligand interaction is of different type. What we are considering that when it is donating to this particular one, that means if we have the sigma donation from the carbon monoxide side, this is the corresponding sigma donation from the carbon monoxide side. So, which is little bit weak, but the corresponding pi acceptance from the metal side is strong, and this particular nature, that means the pi acceptance will be predominating. So, the nature of this ligand or the strength of the ligand, which we will consider it as for classification of there in the spectrochemical series. So, the strength of the ligand will also be controlled by the amount of strong pi acceptance from the metal orbital to the pi star level of this carbon monoxide molecule. So, this we will consider as a synergistic effect, and the ultimate result for this interaction between the metal ligand interaction, which is always there for the metal complex formation, is that due to this synergistic effect we can have more than one bond order between metal and the carbon of say nickel tetracarbonyl or some other complexes, because there are large number of these carbonyl complexes known. So, we have multiple bonding between this metal and the carbon. So, one is sigma, another is phi. So, we have a very strong interaction. So, definitely this strong interaction will tell us that carbon monoxide is a very strong ligand, though we have a very weak sigma interaction, and due to that strength of this carbon monoxide as a ligand, we will be placing this on the right hand side of the spectrochemical series, and we will consider this carbon monoxide as a strong ligand, and we will find that the corresponding ligand field splitting and the corresponding ligand field stabilization energy due to they say delta corresponding delta T or delta octahedron, depending upon the symmetry of these things, will be bigger due to the strength of this carbon monoxide molecule. So, the sigma bond is very nice to know, that is this particular sigma bond is getting donated to the metal empty orbital. Then we have the pi bond back bonding, and another very weak as well as a rare carbon monoxide to pi bonding we can have, because this carbon monoxide molecule can have some filled pi orbitals, and if the empty orbitals on the metal ion is available, because these empty orbitals are available for this donation, that means they are basically the corresponding field level. But if the metal orbitals of this particular symmetry, that means depending upon the metal ion, whether it is chromium or cobalt or titanium or vanadium, if we have some matching this orbital of this particular match symmetry with the carbon monoxide pi bond which is filled, then we can push some amount of electron density, and there we will consider carbon monoxide as a pi donor ligand. So, it can have two good possibilities, that means we can have sigma donation, then pi acceptance from the metal side, as well as we have the corresponding pi donation. So, if there the pi donation is also there, we get something which is above the double bond character, but it is not a triple bond character, but it is above double bond character, and that is why we find a very strong interaction between the metal and the carbon that we all discuss in organometallic compounds, and in some good catalysts or in some other interactions where carbon monoxide or any carbon monoxide type of molecule is reacting with the metal ion, whether it is in from the complex or it is from the corresponding metal bearing catalysts. So, the energy ordering now we can see, because we have to compare this energy ordering with that of the corresponding sigma donation. So, we have this pi which is filled. So, these are all the corresponding levels. So, these are all 6 not 5, these are the 6 electrons in this particular 3 pi level, and these are mostly stabilized, but this particular interaction, that means the corresponding metal for the T2G level is interacting with the corresponding pi star level of the carbon monoxide or the other pi accepting ligand. So, if we have the pi star level which is available, so this pi star level will be interacting with the T2G symmetry from the metal side, and we have the corresponding splitting. So, in essence, what we have seen that for sigma donation, we have been seeing the situation that we have this particular thing when we have this is the corresponding separation. That means the gap between the T2G and EG, the T2G EG gap which we have seen for crystal field theory, and this gap is basically getting modified because the theory we are also modifying. We are moving from a crystal field theory to a ligand field theory, where we are considering a good overlap between the metal orbital and the ligand orbital, and the separation. This particular separation we are considering earlier as the corresponding separation for crystal field splitting, and we are talking in terms of the corresponding stabilization in terms of their CFSE, and that means crystal field stabilization energies and the amount of stabilization. But when we allow some amount of interaction with the ligand, so ligands are coming into picture and we are modifying the theory, and we are now having the molecular orbitals from the ligand side and molecular orbitals from the metal side. And as a result, what we find that earlier we have seen due to the sigma interaction, sigma molecular orbital interaction from the ligand side, we have this particular gap is decreasing, but now this particular gap is increasing when we have the pi acceptor ligand. That means we are getting a corresponding separation, that means the corresponding splitting, if it in terms of the corresponding ligand field splitting, so ligand field splitting will be increased. That means whenever we find a ligand which is of pi acceptor type, that will definitely increase the corresponding ligand field splitting, and that particular ligand should be characterized as a strong field ligand. So, the interaction causes the energy of the T2G bonding orbitals to drop slightly. So, this is the amount of stabilization, that is why we get the corresponding higher energy gap, because the EG level we are not modifying due to this interaction, and which is therefore increasing the size of this delta octahedron. That means we are pushing the electron towards the strong strength side, and the ligands will be of stronger strength. Now, if we compare side by side these two things, that means earlier we have considered that we have sigma bonding as well as we have pi bonding, and if the ligand is of pi type, so if we have pi bonding, so original separation is this, that means this is the T2G separation, and this has been shown for a situation where it is a D3 type of electronic configuration, that means the cobalt 3 system. And if we have the corresponding sigma bonds only, and the sigma bonding interaction, if we just consider it as a point charge interaction, and if we do not have any modification in terms of the corresponding crystal field theory, what we get from there, that this particular thing basically is not modifying anything. But when we go for the pi donor, that means the donation from the pi side is there, and the ligand to metal pi bonding is available, and we have the field ligand group orbitals which is symmetry mass, that means symmetry group orbital or SGOs of 6 electrons. They will be pushed to the T2G level, which is getting for this molecular orbital formation, that means the T2G and the T2G star. So, now this level has basically been pushed from here to here, that means the T2G level is now T2G star level, and the energy gap between the T2G star and EG star has been reduced, and due to pi donation we will be basically modifying this particular energy gap, and whatever we are talking here is the corresponding transition from the T2G star to the EG star level, and this gap is less. That means the ligand, if it is only pi donor type, the ligand strength would be less and it can be considered as a weaker ligand. And the other one which just now we have seen for the pi acceptance, the gap will be increasing because the T2G level is getting stabilized, which is not stabilized like this particular case, but it is stabilized little bit due to the interaction from the T2G empty ligand group orbital, because the ligand group orbitals are empty, because when these are filled we have these are of low energy, but when they are empty this is of high energy. So, when this is filled basically over here we get the corresponding pi donation, and when it is empty we consider these ligands at the good pi acceptor ligands such as carbon monoxide. So, we have metal to ligand pi bonding. So, this particular interaction, because we have this interaction, we have the stabilization of the T2G level, and now we get the corresponding transition from T2G bonding to EG antibonding level. So, we should only remember, because it is also easy to remember also, that whenever we have pi donation from the ligand side, we have the levels involved is both are T2G star and EG star, then both are of antibonding type. But when it is acceptance type, one is of bonding type, T2G level is bonding type and the EG level is antibonding type, and we will be increasing the corresponding energy gap compared to only sigma bonding interactions. So, basically pi bonding interactions can move the corresponding gap from left to right. In one case it can decrease the corresponding gap, and in other case it can increase the corresponding splitting gap. So, that basically gives us the idea that how we can summarize these interactions, particularly the pi interactions. That means the ligands are of different type which can show some pi interactions. So, if the ligands are of only sigma donors, that means they do not have any pi electron, they are mostly forming from sigma bonds only, that means the water molecule or ammonia molecule. So, it is basically providing the sigma donation. That means this donation is not very much affecting the corresponding separation between the T2G level and the EG level. So, the ligands which engage solely in sigma bonding are in the middle of the spectrochemical series. Some are very strong sigma donors. So, if we have the entire spectrochemical series, so at the center basically we will have these molecules as ligands, where it can show only sigma bonding interactions. So, if we have only sigma bonding interaction not of special type, but there are some other special type sigma donors which are very strong, such as CH3 minus and H minus, that means the hydride ion. That hydride ion and methide ion are found to be high in the series. So, they are pretty strong, but they do not have any pi bonding interaction with the metal center. They only show sigma interaction, but their sigma bonding interactions are strong compared to other sigma donor ligands. And then in the second category of these ligands, the ligands with filled p and d orbitals can also serve as pi donors. These are all sigma donors. Then if we have p and d orbitals on the ligand side and which are filled, they can also serve as pi donors, and they basically result in smaller value of sigma octahedron. Then we have the other category, that means the ligands with empty all, that means if it is in terms of the molecular orbital picture, that means the pi star orbitals, or if we have empty p, that means there is no electron in the p level, no electron in the d level, but no electron in the molecular orbital which is of pi type. They are serving as good pi acceptors, that we have seen just now, and will increase the corresponding value of the delta octahedron. So, we have this corresponding series. So, the part of this spectrochemical series we have taken out for this particular justification, that if we have only sigma donors, that means the corresponding sigma donors as this corresponding ammonia and water. So, this can be considered as the typical sigma donor only. So, they are on the central part of the spectrochemical series, because we can also ask that how we can justify in terms of the ligand field theory the corresponding spectrochemical series. So, spectrochemical series what we have proposed earlier in terms of the crystal field theory, but now we are justifying some part because we are unable to explain position of some of these groups such as triphenyl phosphine or carbon monoxide in terms of only crystal field theory, that means only the corresponding charge interaction or ionic interaction, but we should have some covalent interaction for that. And to justify the position of these two groups and some others also like cyanide, nitrogen, etc., we have to invoke the pi acceptance of the ligand side. So, this can only be framed or only we can write when we consider the ligand field theory. So, this is basically the corresponding ligand field justification of the spectrochemical series. So, if we have this water and ammonia, so these are sigma only, and if we have only weak pi donor, so these will be further weaker than this water and ammonia. So, the standard reference, why we are talking all this in case of the standard ligand, because whenever we have, because these reaction kinetics and reaction mechanisms what we will be discussing shortly, that if we have the corresponding ferric ion or ferrous ion taking off 6 water molecules. So, we should have always this particular strength of this ligand. So, the ligand strength is basically is the reference for us. So, not only water, because this ammonia we all know, and ammonia is stronger than water molecule, because we know that if we have this water, if we add ammonia, all the 6 water molecule can be substituted through ligand substitution reaction. So, if this is the reference and we know in terms of this only sigma bonding interactions. So, if we just only count sigma bonding interactions, we see that this is greater than this and we have this. So, if we have this and if we just consider that we can have some other groups like the halides. The halides, all we know that fluoride, chloride, bromide and iodide, and this we all write very nicely. So, they are basically these corresponding weak pi donor. So, they are weak pi donor and they are pi donor, because we do not have anything which is strong pi donor. So, here basically the size, basically why they are, sizes are the main factors. So, in this particular case, so if we just consider this particular size and as well as the corresponding electronic charge, that is corresponding charge on this particular ion can also tell us that why these are weak pi donor and some pi donor ability. But the thing is that where we place the triphenyl phosphine and carbon monoxide, we have this as the pi acceptor. So, compared to all these, basically the pi acceptor ligands are the strongest ligands. So, they are the very strong ligands, and we will find in organic chemistry and other chemical related chemicals for the corresponding complexes, and as the catalyst we find that if you have the carbon monoxide, they can function as a very good catalyst, and triphenyl phosphine also can control the corresponding reactivity pattern of the metal center, and we can have large number of metal complexes as the triphenyl phosphine, because it has a typical steric bulk also and it has the pi acceptance capability also. And so, metal triphenyl phosphine interactions are a very important interaction what we can also study when we will be studying the corresponding reactions, reactivities and the mechanisms. So, we just see in that how we can utilize these things, that means how we can utilize this interaction between these metal and ligand for their corresponding reactions in terms of the corresponding reactivity and the mechanism. So, if we have M and L and whatever we will be talking here is the reactions, that means certain metal ion is there in our hand and that particular metal ion is reacting with the ligand, and how they are reacting, that we want to know. So, how this reaction is taking place? That means we will just, if we know that how this reaction is taking place at this particular standard temperature, how fast the reaction is, or how quickly we can substitute this ligand, whether we can substitute this ligand by L1 or this L1 can be substituted by L2, that basically gives us some idea about the corresponding mechanism of these reactions and the substitutions. So, basically all these things what we will consider in this particular class for the studying the corresponding reactions in terms of their corresponding reaction theory. So, how theoretically we can explain the corresponding reactivity pattern for these different coordination compounds, because these coordination compounds are very important and very interesting also. So, whatever coordination compounds we have, so they have some important characteristics, because all these things, that means the mechanism particularly, because we always must have some mechanism for any organic reaction or any organic transformation, such as how we can get the corresponding benzene is, we can have benzene, how we can get the corresponding toluene molecule, that means how we can add the methyl group to the benzene ring through some Feldkraft reaction. So, very basic organic chemistry reaction, we take some time, we take the help of the catalyst, and the catalyst is sometimes the metal based. So, how we can know that this catalyst is there and this particular one is not behaving as our ligand? That means the metal is the corresponding metal center from the catalyst, and the ligand is the corresponding molecule which is interacting with the metal center and which is getting modified to say L1, that is the L1. So, these are related to all sorts of reactions, particularly the important conversions for any such organic reactions. So, they have some useful characteristics, and there is, because we are talking about all these reactions and we are focusing on attention only on the coordination compounds. So, both organic reactions and inorganic, typical inorganic, apart from these complexes and the coordination compounds, we can have some understanding if we just thoroughly follow the corresponding mechanisms and how the reactions are taking place. But when we talk in terms of the corresponding coordination compounds compared to the very simple transformation of this benzene molecule to toluene, and in terms of very simple other inorganic and organic transformations, these coordination compounds we are calling them as the corresponding complexes, and the nature of these and the corresponding feature of these corresponding coordination compounds are a little bit complex. So, they have some additional features therefore, and we should always keep in mind those additional features when we compare the corresponding reactivity pattern as well as the reactions with respect to some organic reaction or some organic molecule or inorganic reaction or with some inorganic molecule. So, these additional features are very important, that these molecules have more complex geometries. So, not only the complex architecture, that means the presence of the different metals, more than one metal sometimes, and the different types of ligands, and sometimes large number of ligands. That means, when we talk about the corresponding octahedral compound, we have 6 ligands. So, how these ligands are placed around the metal center, because this organic chemistry is mostly dominated by the tetrahedral geometry of the carbon. So, if we have the carbon center, it is basically only the tetrahedral geometry, but the metal complexes can have octahedral geometry, tetrahedral geometry, square pyramidal geometry, trigonal bipyramidal geometry, and much more complex geometries of higher coordination number. So, these complexes have much more complex geometries. So, complexes have more complex geometries, and they have basically more possibilities for rearrangements. So, more possibilities for rearrangement. So, since this feature is much more complex, that means since we have, say in case of octahedral complex, we can have say ligand 1, ligand 2, ligand 3, ligand 4, ligand 5 and ligand 6. So, the direction in which the corresponding incoming group or the new ligand or some reagent is coming, because in presence of catalyst what we are adding over here is the reagent for this sort of transformation. So, it which particular direction, so it will have some directional preference for the reactivity, and if we have the corresponding symmetry for this geometry is not typically symmetric, octahedron is typically symmetric, but it has no directional preference as a result. But when this the same thing, if the same thing is confined in a big biological molecule such as hemoglobin and myoglobin and the metal center is our iron center, then we must have some good sites where the new molecules or the new ligands are coming, such as when O2 is coming into bind the corresponding iron center in hemoglobin and myoglobin. So, it must have some directional preference. So, how this particular geometry, if it is square pyramidal or if it is octahedral only, so how O2 will come and bind this iron center by substituting say some water molecule already bound to the iron site. So, the possibilities are more and we have the rearrangements are also more, and these metal atoms present in these species, it can be the corresponding ions also. So, they exhibit more variability. So, variations are there, more variability in their reactions. So, that means their reactions are also much more complex, and these reactions what we are getting over here is that this particular reaction is not that for the organic reaction, and inorganic reactions are also sometimes pretty simple. So, we have to monitor these reactions very critically, and the reactions what we can have of these complexes are of different types therefore. So, they are of basically 3 types, where we can consider the corresponding substitution, that means the L1 is substituting L or L2 is substituting L1 at the metal site. So, we have the substitution reactions at the metal center, then we have the oxidation reduction reactions or redox reactions. The ligands are all present, but we can take out one electron from the center and we can donate one electron to the center, which is not always possible because we do not have that kind of parallel reaction in case of typical simple organic molecules or inorganic molecules. And sometimes the reactions of the ligands, that means metal is there and ligand is attached to the metal site, and what is happening over there, the reactions of the ligand is basically reacting then without changing their attachment to the metal center. So, the reactions of the ligands. So, if we consider that this particular part is a part of the catalyst, then this reagent or the reactive molecule which is attaching to the catalyst is coming over there and which is attaching to the metal side. So, if the catalyst is basically the support, some solid state catalysts are also known, and if these catalysts are good support. So, on the catalyst support the ligand is coming and sitting. So, after sitting on the catalyst we can have some good modification of this ligand. If it is simple benzene ring, what example we have given just now, that whether we can modify the benzene ring nicely in presence of the catalyst to its toluene in counterpart, or L can be modified to something else which is L1, L2, L3 etc. So, when it is sitting over the catalyst, so we can go for the modification. So, ligand can be modified. So, that basically is our goal, that means how we can change the corresponding reactivity of this ligand side and it can be modified. So, ligand can show this modification of this particular ligand which is bound to the metal sides. So, for all these three types of reactions, this is 1, say this is 2, this is 3, we can have very detailed and elaborate explanations for all these. So, theoretical explanations for all these reactions, how the substitution reaction is taking place, how the redox reactions are taking place and how these reactions are taking place on these molecules. So, we can have such as all these or some more also, that list of known reactions we should have in our hand. So, and then what we want to understand is the electronic structure of the compounds and their interactions. So, if we have the complex or the compound and we want to understand basically the electronic structure of that particular compound, and this particular compound when we know for this corresponding electronic structure, then only we can have some informations related to that of their interaction. So, how this ML interaction is taking place. So, if we find out these interactions with related to that particular metal complex. So, very simple interactions what we can talk about is nothing but the corresponding reaction where we have Mx is reacting with Y, giving rise to the corresponding product which is My plus X. So, this is the very simple reaction. If we have the ligand as X or anything else which can be substituted by Y by L1. So, we get the corresponding complex Y M L1 will be there and the existing ligand which was L will be kicked out from the medium. So, if we have this axis as the corresponding free energy change for the reaction, that means for substitution reaction, substitution of X by Y, and how much we are progressing from the left to right, that how fast or how quick is the reaction or how far the reaction is going, that means the extent of reaction. So, if we just find the corresponding extent of reaction, so we get this change only if we have a corresponding potential energy profile or potential energy surface for this reaction is like this. So, what we have that Mx plus Y is interacting, which is here in terms of its free energy. So, we will be gaining some free energy change, the free energy change will be negative and the reaction would be spontaneous. So, from this free energy axis we should have some gain from the free energy and we are getting this particular product. So, what we get there this particular, because we have to cross something, some barrier has to be covered. So, this is the corresponding transition state, and we will consider also more as the corresponding transition state theory, and this is the corresponding free energy change, and we consider as the corresponding free energy of activation delta G dagger. So, this is the free energy change of activation for the reaction. So, we can measure, we can find out these parameters, and ultimately we can know the exact form of these reactions and its mechanisms. Thank you very much.